Hey everyone, so before we move on to another variable that we can talk about when it comes to linear motion, we're going to talk about something else, which is called motion graphs. In particular, we're going to start off talking about position versus time graphs. So as the name implies, these are going to be graphs that represent the position of an object, or it could be displacement of the object or the distance that the object travels over a certain amount of time. This is a really nice way of getting a lot of information, and the thing that we want to figure out is what type of information we can get out of it, and how do we get it. So let's consider this. We have two swimmers. We have Adam and Ben. There's a 50-meter long pool. We have Adam that initially starts at one end of the pool, traveling with an average speed of 2 meters per second, while Ben starts at the other end of the pool and travels with an average speed of 1 meters per second. So if we want to sketch the position versus time graph for both swimmers, what would it look like? Well, first thing that we have to figure out is where are their initial points? Where are these two objects at time equals 0? So what we have is both of these are starting 50 meters apart. Now this kind of goes with the whole setup of which part are we going to designate as our reference point. So we said that here that they're both starting at both ends of the pool. It doesn't matter which one we set as at what location. So we can actually say that Adam starts at 0 and then Ben starts at plus 50 meters on the other side of the pool. It's not super clear which side's which, but this is going to be important as far as when it comes to directions and stuff. All right. So what we're going to end up doing is putting some of this information onto a graph. Now, another thing that we want to keep in mind is the fact that the speed is telling us how much distance is being covered every second. So when we say that Adam travels with the speed of 2 meters per second, what that's really telling us is that every 2 meters, every second, Adam travels 2 meters. So in 1 second, he travels 2 meters. In the second second, he's going to travel 4 meters, and so on and so on. Likewise, Ben is going to have the same thing, but this time it's going to be 1 meters per second, but in the other direction. Um, so, like I said before, we're going to have Adam start at 0 and then Ben starting at plus 50 meters because they're 50 meters apart. Now, like I said, it doesn't matter which one we define as 0. The only difference, like I said, it wouldn't really matter so much here because there's no picture that tells us, that one has to be on the left, one has to be on the right. But if we did have a scenario where we had like a diagram that showed that Adam was on the left side of the pool and Ben was on the right side, then if we did say that Ben was 0, what would happen is Adam would be sent to negative 50 meters. So again, it just really shifts the graph, but nothing really changes about anything else. All right. So moving on, Adam's graph would end up looking something like this. So we have him starting at 0, and that's the first point that we want to make sure that we label. And then every second, or in this case, every 5 seconds, we're going to note that Adam travels a distance of 10 meters, right? Because he travels at 2 meters per second. So after 5 seconds, it's 10 meters. Then after 10 seconds, it's 20 meters, and so on and so on. So his position graph would look like this, starting at 0, going all the way up to 50 by the time it reaches 25 seconds. On the flip side, Ben's starting at positive 50 and he's going towards 0 because he's going towards Adam. So his graph actually should be going downwards. So he's going to start at 50 and then every 10 seconds now, it's going to go down 10 meters because he 1 meters per second in the other direction. So his graph would look like this, starting at positive 50, going all the way down to 0 after 50 seconds. Now, why is this important? So there's a lot of reasons why we would want to do this. First off, it can help visualize or better visualize more complex motions. So if we have an object that is constantly undergoing different velocity changes, if we have multiple objects, traveling, this can help kind of clean it up and also give us a lot more information and show this information in an easy to grasp way. It can also tell us information about uh, the situation in the sense of, when would these two objects end up meeting or passing. For example, if we wanted to figure out when Adam and Ben actually cross paths with each other, when they are swimming towards each other, we can actually put both of these graphs onto the same plot, and then from that graph we could actually see where they cross. And we are also going to have to be able to go and look at a graph and come up with a verbal description of what's going on, or vice versa. You might have to be given a verbal description of what's going on and come up with a graph based off of that. So it kind of develops that skill of understanding what a graph looks, what the graph should look like for any given scenario. So it's a major thing to understand what a position versus time graph should look like for any given scenario. All right, so here's our first question. Pause the video, work stuff. We'll go over in a second. All right, so for part A, it wants us to determine an equation for the position as a function time for each swimmer. All right, so this is one thing that we're going to have to work on, is the fact that we have to come up with our equations for this. Now, the only real equation that we have as far as the position for an object is going to be the average speed equation, right? We have the average speed or average velocity equals displacement over time, or change in position over time, if you will. So what we're going to end up doing is we're going to end up rewriting this equation like this. Now, let me actually, there we go. Where does this equation come from? It seems a lot more complex than what we have. Well, this comes from the fact that the average speed, or sorry, average velocity is the change in position or the displacement over time. If I move the time over to the other side, I end up having this. And then I could replace this change in position or displacement, because they're the same thing, with the final position minus the initial position. So moving this over to the other side, we end up getting that the final position of an object will be equal to its initial position plus the average velocity times time. And this kind of makes sense, right? The position of an object will be based off of where it starts, and then also the distance that gets covered by its movement. And this velocity would it matters whether it's going left or right, positive or negative, and that would change my final position. So this is what the equation will end up looking like. We have this for atom, and we're just going to plug in the numbers for x naught a, which is going to be the initial position of the atom, the average velocity of atom, and then we're going to leave time as a variable in this case. So when we plug in that atom starts at initial position 0 with an average velocity of 2, we end up getting this. So 2 meters per second times time will give us the position of atom at any moment of time. And if we actually look back to the graph that we made for atom, we find that if we were to put this into our graphing calculator, it matches the graph that we had made for atom before. All right, let's actually erase all this before I move on. And then when we go to do for Ben, this time we have to be a little bit careful, because this time Ben actually starts at an initial position of 50 meters. So this number is going to end up being 50. And then the other thing that we have to be careful about is the fact that the average velocity of Ben isn't just 1, it's -1, because he's coming in the opposite direction. And that's why the graph ends up having that negative slope to it. So when we plug in the numbers, we end up getting 50 minus 1t, which again, if we were to plug it into the calculator, we would actually see matches what we got. That Ben starts at a position of 50 meters, the other side of the swimming pool, and then decreases over time, because this term starts subtracting more and more from that 50 until it goes to 0. All right. And then here's the next part. So they want us to calculate the time and position of the two swimmers when the two swimmers end up passing by each other. Now, they want us to figure this out in both ways. Either, well, they want us to first figure out with equations, but then they also want us to use our graphs for this. And I kind of already hinted at to, how would we find the moment that they pass each other using the graphs. So we're going to start with the equations first. Now, in order for them to meet, that means that their final positions have to be the same. So what I can do is I could take those two position equations and I could set them equal to each other. So I know that the final position of Adam and the final position of Ben are equal, because that's what that means. If I imagine that the pool is on a giant graph with one end of the pool being at 0 and the other end of the pool being at 50 meters, then when they're both at the same location, the x position will be the same. So if I set the two equations that I came up with equal to each other, I can solve for time, and I end up getting that time will be equal to 16.7 seconds. Now that I have this time, I can go back to pretty much either of the equations and figure out what position they are at. So I'm going to use the simple one, Adam, and I'm going to plug 16.7 into his equation, figure out where he is, and we get that he's located at 33.4 meters. Now, I could always check and test it to see if gives me the same number. It should. If I were to do 50 minus 16.7, I should end up getting a number that's essentially close to 33.4. Now, why is it not exactly 33.4? It's because that time is actually rounded. Realistically, I rounded the time to 16.7 instead of 16.666666667, and so on and so on. So, the number is going to be rounded a little bit, but it's close enough. All right. Now, as far as using the graph, we're gonna, like I said, pretty much do the same thing. We're gonna take our graphs, and I had mentioned that you can overlay them onto the same graph, which is what we have here. So I had to change the graph a little bit for them. In particular, the thing is, Adam ended up covering more distance much quicker, and technically his graph would actually keep going on and on. But we know that the pool actually has a maximum size, so once Adam gets to 50 meters, his position should actually just stop there. He reaches the other side of the pool, so it shouldn't be increasing or changing at all from there. And then we have bends going from 50 all the way down to 0, the other end. So this is what our graph looks like, and we can pinpoint that right here is the moment when they cross paths. Now it's hard to actually tell, mainly because this graph has no real divisions. It's really hard to see exactly where this point is. But if we recall what we got in our calculations, that the time was 16.7, this is about where 16.7 would be on the time axis. And then the position was 33.4, which is about a third of the way between these, which is what it looks like. So yeah, our graph gives us the same thing. Now, if we had more accurate graphs, then we'd be able to tell this point a lot better. In fact, if you had a graphing calculator and you actually graph these two lines, you can use the intersection function, intersection calculator on your graphing calculator to actually figure out exactly where these 2 points cross. So just keep this in mind, that this is something that you actually have at your disposal to answer some of these position versus time graphs. All right, and I'm going to leave it at that. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.